Hello? Can you hear me?
Yes, Professor. Okay.
Let's follow our schedule. How many presenters are today? We plan Alexander Rusnak. Alexander. And then Svetlana Kuchuganova. Svetlana.
Yes, I'm here.
Mm-hmm. Walid Koliai.
Yes, I'm here.
Great. Then, except of Dinesh, Mukul.
Yes, I am here.
Okay. Raphael Blankson with Thesis.
Yes, Professor.
Okay. Maxim Kachanov.
Yes, I'm here.
Okay. And Kazanets Roman.
Hello, I'm here.
Okay. So let's start from Alexander Rusnak. Are you here, Alexander? Okay, let's start from Svetlana Kuchuganova, please.
Okay. Can you see my screen?
Yes.
Okay. Greetings to all. Today I will present my bachelor thesis, application of Mixup-Breakdown algorithm to improve speaker diarization. My scientific advisor is Evgeny Nikolaevich Pavlovsky. First, what is diarization? Diarization is the process of dividing the incoming stream into homogeneous segments in accordance with the belonging of the stream to one or another speaker. Diarization answers to question who spoke when. And it can enhance the readability of an automatic speech transcription by structuring the audio stream into speaker turns, and when used together with speaker recognition system by providing the speakers through identity. Speaker diarization is a combination of speaker segmentation and speaker clustering. About recent advances. In the early years of the use of diarization technologies, the focus was on unsupervised segmentation and clustering, including not only the speaker's speech, but also the background sounds. Since the advent of deep learning, a significant number of experiments have been conducted to investigate diarization using neural networks. Some typical examples are speaker embeddings such as Y, X, and D vectors. At the moment, the following areas of research can be discussed. Classical modular diarization system with a deep learning model, end-to-end system based on deep learning, and other. Let's start with first and classical modular diarization system. You can see a diagram of most modular diarization system on the slide, and I will talk a little about each model. In the front-end model, there is an improvement in the quality of the signal, dereverberation, normalization, separation of noise from voice activity, and deep learning approaches have shown the best results. For example, LSTM-based approaches. Then speech activity detector distinguish speech segments from background noise. Usually set consists of two parts. The first is used to extract features from audio frames, for example, Kipsral coefficients. The other part is a classifier that predicts whether the input frame is speech. The performance of the set significantly affects the performance of the entry-diarization system because it can generate a significant number of false positive events or skip speech segments. Then segmentation. In the process of segmentation, the incoming audio stream is divided into several segments, which are further assigned speaker labels. There are two ways to perform speech segmentation for diarization task. Either with speaker change point detection or with uniform segmentation. Segmentation based on the detection of the speaker's changeover point has been replaced by uniform segmentation as the varying segment length created additional variability in the speaker's presentation, which degraded the accuracy of the speaker's presentation. Embeddings. Early diarization systems were based on Gaussian mixture models embeddings, building acoustic signatures based on small Kipsral coefficient. Further, with the advent of deep neural networks, such embedding as Y, X, and D vectors appeared. The most widespread is the D vector. To extract it, the composite function of a set of filters and several fully connected layers are used. After generating the speaker representation for each segment, clustering algorithm is applied to make cluster of segments. Use algorithm like mean-shift clustering, agglomerative hierarchical clustering, and spectral clustering, and other. And finally, post-processing. During post-processing, the boundaries of the speaker are clarified, the stage of multiple direction are merged, if any. More recently, Dover diarization output voicing error reduction method was proposed to combine multiple diarization results based on the voting schema. Some about Dover. In the Dover method, speaker labels among different diarization systems are aligned one by one to minimize their diarization error rate between the hypotheses. After every hypothesis are aligned, each system voids its speaker label to each segment region, and the speaker label that gains the highest voting weight is selected for each segment region. About deep learning approaches. First, joint segmentation and clustering model. A model called unbounded interleaved state recurrent neural network was proposed that replace the segmentation and clustering procedure into a trainable model. Given the input sequence of embeddings, with CNN generate the diarization result as a sequence of speaker index for each time. Joint segmentation, embedding, extraction, and resegmentation. In this method used region proposed network. It jointly performs segmentation, speaker embedding extraction, and resegmentation. The EPN was originally proposed to detect multiple objects from a two-dimensional image, but one-dimensional variant of the EPN is used for speaker diarization. EPN works on the short-time Fourier transform features, and neural network converts the STFT feature into the feature map. Then for each candidate of time region of speech activity called an anchor. The neural network jointly perform three tasks. First, estimate whether the anchor includes speech activity or not. Second, extract speech embeddings corresponding to the anchor. And third, estimate the difference of the duration and center position of the anchor and the reference speech activity. This task is segmentation, speaker embeddings, extraction, and resegmentation, respectively. Some about joint speech separation and diarization was Condos-Bastian proposed to incorporate the speech activity model to speech separation based on the spatial covariance model with non-negative matrix factorization. They derived the EM algorithm to estimate separated speech and speech activity of each speaker from the multi-channel overlapping speech. And while their method jointly performs speaker diarization and speech separation, their method is based on statistical modeling, and estimation was conducted solely based on the observation without model training. And Newman later proposed a trainable model called online recurrent selective attention network for joint speech separation, speaker counting, and speaker diarization based on a single neural network. And fully end-to-end neural diarization. Recently was proposed framework called end-to-end neural diarization, which performs all speaker diarization procedure based on a single neural network. Architecture you can see on the slide. There are multiple languages of EEND. Firstly, it can handle overlapping speech in a sound way. Secondly, the network is directly optimized toward maximizing diarization accuracy, by which we can expect a high accuracy. Thirdly, it can be retrained by real data, just by feeding a reference diarization label, while it's often not straightforward for the pure works. But on the other hand, several limitations, also known for END. First, the model architecture constrains the maximum number of speakers that the model can cope with. Secondly, EAND consists of BLSTM, of self-attention neural network, which makes it difficult to do online processing. And thirdly, it was empirically suggested that EEND tends to overfit to the distribution of the training data. About my algorithm, Mixup-Breakdown training. The Mixup-Breakdown strategy is inspired from the fact that a human auditory system is capable of separating source, not requiring any client source for learning, yet having high consistency to perturbation. As illustrated in the algorithmic flow of MBT, we explore the interpolation between separated signals to provide a perturbation strategy to maintain the consistency of learning. We first introduced the mix out and breakdown operation. You can see it on the slide. and Mixup-Breakdown strategy trains a student model FTTS to provide consistent prediction, which the teacher model FTTT of the same neural structure at the perturbation of predicted separation from the input mixture. The semi-supervised learning model with a labeled dataset and an unlabeled dataset looks like this. Mathematically, the MB operation can view as a generic augmentation of the empirical distribution. Here you can see correctness loss, consistency loss, and RAM function that increases the importance of the consistency term as the training goes. And goal is my bachelor thesis is improve the quality of diarization with Mixup-Breakdown training. We have broken this goal into subtasks. The first task is obviously to realize Mixup-Breakdown training because it is not in the public domain. Then we need to adapt the Mixup-Breakdown training for the task diarization since it has only been used for speech separation. And finally, the analysis of the result will be carried out and possibly the replacement of the backbone with a newer neural network, for example, WaveNet. At the moment, we generated datasets from LibreMix and FAM noise. It consists from speaker plus speaker, noise plus speaker, and two speaker plus noise. Then we implemented MBT version 0.1, and the model was trained with the Mixup-Breakdown algorithm and the Convtas network as student and teacher model on two datasets, speaker plus speaker and speaker plus noise. Further work, it is test on AMI dataset because it is benchmark datasets for its problem, and compare results of MBT, TASNet, and Spectra cluster. Then consider options for replacing TASNet with newer models, generalize the results by 3, 4, and more speakers, and publish the code on GitHub. It is all. Thank you for your attention.
Thanks. Any questions? I have a question. What the most hard part was in implementation of the network?
MBT training or?
In the whole work.
Is to adapt separation result to diarization.
Mm-hmm. Okay. Other questions? It seems no questions. Then thanks for presentation. Thank you. So the next speaker is Mukul Wishvas.
Hello, everyone. Let me share my screen. So, are you able to see my screen?
Yes.
Okay. So, hello, everyone. Today, I'm going to present my master thesis. So, the topic of my master thesis is recognition, feature space representation, tracking, and performance in DCNN driven safety system. And my scientific advisor is Mr. Alexei Ofini. So, let's start. So, we started this thesis when the pandemic just started, and it was in the early stage. So we come up with an idea to create a face mask detection algorithm, but I already talked about it. So we try to extend this method to a new we try a new approach in it, and we try to implement how we can track those people who are entering the building with wearing the face mask, and they remove after they enter in the building. So it's this type of this type of research called person re-identification problem, and we try to do the same with the face mask detection. So this is the architecture of the complete project. This is the this is how the end project will look like. So we have face mask detection model. So it will receive the input from the camera, and this will detect whether the person entering the premises is wearing face mask or not, or correctly or incorrectly. After that, it will generate a bounding box on the person, on the complete person from head to toe, and based on that bounding box, we will crop the image and store it into the database, and those images will flow to the person re-identification model, and it will check on every non-overlapping camera which is installed different places, and it will check whether the same person is wearing the face mask or not while going through the uh, vision from sorry, if he moves from the vision of camera 1 to the camera 2. So we can simply track the person. He is following the hygiene procedure or not. So as I told you in my previous presentation as well, that we use detection for this model, but we didn't just simply choose the detection model. I tried to implement the same thing on Detectron 2 as well, but we got better accuracy in detection, which is 0.158. It is greater than the MAP of Detectron 2. So that's why we choose this detection framework. And we also have a few advantage over it. So it support multiple data set. For this, I choose COCO data set because it was easy to create, and we can train model in a better way. Also, it runs on GPU, so it will be much faster. And so let's talk about what is re-identification problem. So as I already told you about it, so we will track a different person on non-overlapping cameras. So to explain it in a simple way, if we have a camera on first floor and another camera on second floor, so we can track person going to the first floor and sorry, in the vision of first camera and in the vision of second camera, but we don't have the connection to say that both are the same person. So I tried to create a connection and to track the both person are the same and wearing the mask, or just remove the mask while going from floor 1 to floor 2. So for this, I used the Torch ReID. It's a library implement in PyTorch. So this is how the library is constructed. So it has 7 different modules, and let's talk about little bit about Torch ReID. So in data, we have data loader, data augmentation method. Here we can define how our data loader should be created, how many batch we want, and what type of augmentation we want to do with the image data set. And for the second module, we have losses. We can define different type of losses, BCE or triplet loss. We can choose from it. Matrices. For this, we can use cosine distances or Euclidean distances to differentiate different images and model. So we have a lot of variety to choose from. We have a ResNet, a complete family of ResNet, VGG, and some new ImageNet and new families as well. And they continue to continuously improve this model so that we can try and implement with the current version of feature extraction model. And optimizer is to create the optimizer and the learning rate. Engine, it will take all this method and run the training for us, and it also have evaluation pipeline as well, so we can choose how our model is performing. And utils, it's just to visualize all the results we got while training. So a little bit about annotation. For the annotation, I use ImageMe data, sorry, ImageMe tool. So that's the screenshot how the image was annotated. So you can see we annotated the complete person, so we can have a bounding box around the complete person. So that's this is the annotation. So at first we just annotated the face of the person, but we think to annotate the complete person so that we can later crop the images and send it to the re-identification model. So on the left hand side you can see the output of the first model, and on the right hand side you can see the output of second model with the bounding box on the person. So for re-identification and for face mask detection, we create our custom data set. So these persons are from SCI college. So you can see we tried different resolution for to train the model, and we annotate we collected total 21,127 images. So from top to bottom, you can see resolution is decreasing as the person moves away from the camera. So we have a huge variety of images to train the re-identification model. So let's talk about some experiment and result. First, I tried VGG16 to to get the features from the images, and use cosine distances to get the similar images. So on the the image which is on this single image is the query image, and below these 5 images are the result image. So if I use VGG16 for feature extraction and cosine distance for to get the closest images to the query image, I got this result, but this is not very reliable. As per this experiment, I can say VGG16 able to extract the posture and the color of the dress the person is wearing, and those features are more dominant. So we got this type of result. If the person is wearing white t-shirt, it return the person who is wearing white shirt or t-shirt. So this was not a good approach to go on with. So for the next approach, I tried structure similarity index. It will choose which images are more close to each other structure on basis of the structure. So this was also not very good approach because it just returned those images which are very similar to each other. If the person is moving away or just the lightning condition are changed, it is not able to give exact matches. So we we are not able to continue with this method, and we move on to ResNet 50. And with ResNet 50, I use cosine similarity. It's able to give result, but these results are not so good because it return some images which are not close to the query image. So we drop this idea, and I use Pearson similarity. It able to give some similar result. As you can see, this is single positive match, but other results images are completely irrelevant to the query image. So we also drop this Pearson similarity as well. And this is the ResNet 50 with Jacquard similarity. The very curious thing about Jacquard similarity is it's able to return the images if the query image is very dark. So it's able to return those images which are very dark. So it's basically dominant on the pixel colors. So that's not a very good result. So we also drop this. Apart from this, I use ResNet 101 as well, but there are no significant return results in that direction as well. So after that, we use torch reid. So with torch reid, you can see on the left hand side we have query image. On the right hand side there are 10 results, which is very close to this image. And after using this method, we are able to receive 68% accuracy, which means in this 10 result, 6 images are positively matched with the query image. And if we do a random search, in that case, we will receive only 2% accuracy. So in the top row, you can see the image is very blurry, query image, but it's able to return 1, 2, 3, 4, 5, 6 exact match. And on the second image, this image is more blurry, but it's able to return 5 to 6 positive matches. And you can see here this image is more blurrier than the previous two, but it's able to return 4 positive matches. And this one is better resolution as compared to previous one, but here it's able to return 1 positive match, and other are red colored women, but there are not positively matched. But this you consider this came under remaining uh, 32%, which are false negative. And for the publication, my abstract for this face mask detection was accepted in MNSK NSU 2021, and based on my research, I submitted my paper on IGISRT, which is International Journal of Innovative Science and Research Technology, and it got accepted. And they will publish it very soon, and I will submit the certificate as well. And yeah, that's all about my thesis. So if you have any question, you can ask.
Yes, I have a question. What is your scientific contribution?
Yeah, so this is the first attempt to join object detection model and re-identification model together. So it can be used in various scenarios. Suppose it can be used in airport and any security places. It can be used for places where where a person is lost in a very big place like a stadium, and if it came into the vision of second camera, so we can focus our search in that area, so he can be found very soon. So this so this is the first type of approach to join these two models.
It doesn't look true because it's obvious to use after re-identification to use object detection model. It's usually used. Actually, have you trained your model to achieve better score in re-identification problem?
Yeah, actually, for person re-identification model, our data needs to have camera ID, person ID, and as we have 21,000 images, we are not able to give person ID to each and every images. So this was the major challenge in front of us. So we used. So for the
What you
initial
use?
sorry, what?
What you used?
Okay, so we have to manually annotate around 20,000 images for person ID. Like if a person has 1,000 images in that data set, we have to find 1,000 images and give them the same person ID to train the
Yeah, I
model.
know. So you used pre-trained model.
Yeah,
And what? Yeah, on which data set it's
it's
pre-trained?
on Mark 1501.
Okay. Yeah,
So,
I know.
so this was the initial result for Mark 1501. This is our initial step, and we will include chunk data set as well. So we will have a big data set, and our model accuracy will be increased. We are hoping to increase it more than 60%.
Oh, okay, but like, where is a comparison? Comparison with some public available data sets like CUHK
Yeah,
03. Yeah, check. So what the score you have on these data sets?
Okay, so we are not able to train this model with our own data set. That's why we are not able to provide any comparison with the benchmark data set.
Yeah. Okay, so I understand. Your main contribution is joining these components into one safety system.
Yeah, we are trying to create this data
And
pipeline.
what's the total quality of this pipeline? How you justify it's good, bad?
Okay, so for as this is the first initiative to create this one, we try to merge these two model, and with merging these two model, we are able to get in top 10 return images, closest images, we are able to get 68% accuracy. Like among the top 10 results, 6 to 7 are positively matched.
Positively match on re-identification or
including both, including
or
face
mask
detection
querying and mask
yes.
detection.
So here you can
Okay.
see this lady is wearing face mask, but it is positively matched with the query image. So this is the joint accuracy of both the model.
Okay, I understand. Okay, thank you for presentation.
Thank you very much.
Let's go to the next. Walid?
Yes, do you see my screen?
Yes, now we can see.
Just a second. So hello everyone. In today's presentation, I'll be talking about my thesis, data-driven online assessment of 2D particle image displacement using GPU. So as a quick reminder of the purpose of this project, so basically we want to study and get quantitative information on flow characteristics. The work is based on an algorithm technique called particle image velocimetry, PIV. This technique is not based on any simulation. We actually perform the experiment to see the flow, like we can see on the image on the right. So the images of the flow are captured and then manually post-processed and analyzed using cross-correlation approach. What we want to do is to perform a real-time PIV, not a standard PIV. So for that, after the images of the flow are captured, they will be post-processed and analyzed, not manually, but automatically. And for that, we'll be using a trained neural network model. So the neural network model will take a pair of images as input and output the appropriate velocity field. So the main tasks are to select an appropriate neural network model, train the model, implement a software for image streaming from the CCD camera, for capturing the images, and finally test and analyze all of it. So for now, we mainly found 3 appropriate models, and we are currently working on the PwC net model. So before training the model, we obviously had to select data sets, pre-process them, prepare them in order to actually use them to train the model. So we selected multiple data sets. We found some data sets that comes only with inputs, so there wasn't velocity field for the inputs. So in order to take advantage of those data sets, because we needed more data in order to train the model, actually the only selected or the only data set that we found wasn't sufficient enough. So we thought to implement an algorithm that would produce velocity field for a pair of images. After that, we pre-processed and prepared the data in order to train the model, which included some data cleaning and data transformation. Let me show you some general examples. So first, the selected data sets, just to have an idea, insight. So here are some of the selected data sets. So for example, the DNS turbulence data set. We can see that the inputs are in TIFF format and the outputs comes in a flow file. So for example, this one contains 2000 rows, the next one around 2000, 600, etc. So for the data pre-processing, let me show you. Again, let's take the DNS turbulence as an example. So for the data cleaning, the main idea was to sort the data set, check for missing data, and drop duplicate values. We didn't actually work with pandas data frames. This is just an example. For example, by checking the duplicate values to compare two images, we had to compare them pixel by pixel. For data transformation, so the data sets comes in TIFF format, and actually the model takes inputs as a ppm format. So we had to convert from TIFF to ppm. Now for the algorithm that we talked about, so here's an example of a PIV dataset that comes only with inputs, like we can see here. So like we can see here, there is no outputs. We had to implement a solution that would provide us with velocity field for a pair of images. So for this, we used different methods. We can see that we started here by not having, I would say, a really good quality result, as it contains squares and is it really fluid. We managed to have a slightly better result after that until coming up with the wanted result. Maybe it doesn't look, let me show you a bigger picture. So as we can see here, we started from this, from squares, and we worked our way until having this one. I'm not sure if you can see the sprinkles, but this is a pretty good result. Now for the training, so I prepared, normally everything I prepared it 3 days ago, so let me show you. So we managed to load the data sets, normally stuff. This is the configuration. So we managed to obtain or to gather around 13,000 data for the training and 400 for the validation. So we configured the training, everything is working fine. We created the model. The only thing left is to train the model. I actually started training, but I wasn't able to finish it yet. I had some issues. For some reason, I couldn't use GPU in Google Colab. Maybe it's because the model is using an older version of TensorFlow, I'm not sure. But even when you're using the CPU, when I finish it, it keeps running out of time in the middle of the training. And my good connection, internet connection doesn't help. But basically that's what's left. So I have to train the model and see how it goes. I will have to run it offline with my CPU and see how it goes. That's basically it for my presentation. Thank you for your attention.
Thank you. Questions? Where does the data come from?
Sorry, where does the data come from?
Yes.
I found some in a well-known site for PIV, like the one I showed you, where I applied the algorithm on it. That comes without inputs. And for the other ones, I found some on some papers that use the same approach, and some in some websites.
What is mathematical evaluation criteria you have? You said that the image is pretty good if you look at it by eyes, but mathematically, what is the criteria?
I don't have an exact criteria, but basically we have to compare it to a standard PIV. So if we apply an already existed algorithm, well-known algorithm that perform cross correlation, the result is pretty similar.
Yeah, we must refer to some quantitative metric.
Yes.
Maybe several people looking at image and expert by their opinion, mean average opinion.
Yes, I'll do that.
Okay. Thanks.
Thank you.
Interesting looking presentation. And we continue with the next presentation from Raphael Blankson and his studies.
Hello, can you see my screen?
Yes.
Good evening, everyone. I'm Raphael Blankson, and I'm presenting my thesis, applying variational circuits in deep learning architectures for improving discriminative power of speaker identification embeddings. My supervisor is Evgeny Pavlovsky. Okay, so this is the overview. I think I've already presented the first part already in the last seminar, and I would continue with, after that, I will just give the latest update or changes that have been done. Quantum machine learning is just, in simple terms, we can just say it's the intersection of machine learning and quantum computing, like bringing the power of quantum computing into the already powerful machine learning environment. For the background of study, some of the things that you have to be familiar with in order for you to be able to comprehend this thesis. I'm just keeping it short. Variational circuit, which is like a form of quantum algorithm that involves both classical computing and quantum computing, because as at now, we don't have a full fault tolerant quantum computers, like where they don't make errors. So we have to resort to a different form of quantum algorithm that can help us solve quantum problems. But variational circuits themselves are not as powerful right now as classical computers. So we'd have to combine them. That's where the algorithm comes from. So you have to combine them with classical algorithms to get some power. And embeddings in quantum sense is just the way we map classical data into the quantum environment. And there are several forms of embeddings, but as at now, to choose a particular embedding, the best embedding for a particular problem is still an open research that you would have to try to find out which one works best for you. So just as I explained, this is an image of variational circuit, and this is how it would work. So first you have your features in a classical environment, and you prepare it, like which is the embedding onto the quantum circuit. And then from the quantum circuit, the output of the quantum circuit is sent to the classical computer for processing and optimization, and then back to the quantum circuit. So it's an iterative process which goes on and on and on to, unless you get the cost minimized and the results you want. Right now, machine learning has been very powerful in solving a lot of problems in our daily lives, reinforcement learning, computer vision, natural language processing, and the likes. But as at now, data set is actually growing at a very fast rate. And now with the event of 5G technologies, the speed up and amount of data is growing. We need to find ways to actually be able to process these data and also be able to make meaning, and our machine learning algorithms work with them. And this is where quantum machine learning come into play, because with the power of quantum computing, with the current power of machine learning, amazing things are going to happen. And for the reason why we are trying to apply this into the audio domain is that quantum mechanics actually deals with particles in a waveform, and audio data in itself is a form of wave. So we are assuming that since they're both waves, then there could be some benefit when we apply them. But as of now, there's no quantum application on audio data yet. So the purpose of this research is we are trying to investigate if we apply variational circuits to speaker data, there could actually be increased performance or not. Or how can quantum computing help in the generalization of classical machine learning algorithms? And we limit this research using photonic quantum circuits, or quantum computing that deals with Q-modes. Some limitations currently in the quantum realm when it comes to quantum computing is like we don't have infinite number of qubits or Q-modes, but they are limited. And there's no perfect quantum hardware, as I mentioned earlier. And so we need to resort to these near-term quantum computers that are not as powerful in themselves as classical computers. And for the photonic domain that we are dealing with, there is no actual quantum computer that can process machine learning in that domain. The photonic computer that is currently available in the world is owned by a company called Xanadu, and they are not yet ready for quantum machine learning task. And also, so we need to use simulators. But then when you have to simulate quantum algorithms on classical computers, it's very costly and slow. And also coming out with quantum algorithms that can actually outperform classical computers to achieve what has actually given quantum computing the buzz, which is called a quantum advantage. It's very difficult to do. Some of the definitions that you would have to be familiar with, like qubits or Q-modes, which are just a basic unit of computation in quantum computing. You have gates that are the building blocks of the circuits, and the circuits are just it's just a model of quantum computations. Then we have Fourier transforms. Because we are dealing with audio domain, Fourier transform is a mathematical concept that is used to kind of decompose an audio signal, any signal, into its frequencies. Fast Fourier transforms is a form of Fourier transform in that it deals with a discrete form of signals. And like going further forward, spectrogram is a visualization of audio signals. So these are the images, like you can see here that the raw image is a wave, and it's spectrogram how we picture this, and this is MFCs here. So some literature that I reviewed. In this project, we are going to apply transfer learning, but bringing quantum computing into transfer learning opens the door for more opportunities in transfer learning, because currently the transfer learning that we have is like you have, the idea is like you have a data set and then you train a model on it, and then you apply it to a specific data set. Either you do feature fine tuning, which is like you try to take some part of the last part of the model off and then train it on a new data set, which is like a classical pre-trained model on a classical new data set or new problem. But when quantum computing comes into the space, there are extra 3 ways that this can happen, where you can have like your pre-trained model can be a classical algorithm, and then the new task will be a quantum, which is a classical quantum transfer learning. You can have your pre-trained model as a quantum network, and then your new task as classical, which is quantum classical. And then you can have a quantum transfer learning approach where both the pre-trained model and the new task are quantum tasks. But we are going to, this experimental thesis is based on the classical quantum approach. Another review, like what is going on here, is like a continuous variable neural networks, which is a form of, which is like in the photonic space. These authors argue that because these have higher Hilbert spaces, they have the natural tendency to mimic what we do in classical machine learning tasks. So we can actually use these techniques to create like a fully connected layer, recurrent neural networks, convolutional neural networks in the photonic space that works just like in the classical machine learning space, other than the popularly known qubit space. In that sense, because they are discrete, they deal with discrete space, and machine learning problems actually continuous. They are not able to model it very well like the photonic ones, and most of the time it's try and error. And these are supposed to give better results than the qubit ones. So from here, it is the fully connected neural network in the photonic quantum computing is just having to deal with some interferometers, which is made up of local displacement and squeeze gates, and then displacement, and then you use a nonlinear transformation, which is over here is a non-Gaussian gate that makes up the fully connected layer in the qubit space, in the Q-mode space. And for the audio signals, there are actually a lot of papers I've reviewed, but I'm just trying to keep them short here. So in this paper, they try to let us know that as many areas have benefited from the power of deep learning, so as an audio space too, it has outperformed the traditional methods that we have in the signal processing space. So, and they also show that unlike images, which are two-dimensional, audio data is just one-dimensional, and they have to be studied in a sequential order as well. So the traditional way of processing audio data is like you have to manually perform feature engineering, extract the XTFT, and then extract time and frequency features from the data, which is prone to errors and also not very fast compared to using deep learning approaches. So deep learning actually came in and made the process simpler. So you just have your raw waveform, and then you use your deep learning, or you extract images from it, and then use your deep learning model so that it can learn from the data itself without any feature engineering. So for the methodology that we're trying to use, as described, we use the quantum neural network from the continuous variable space, which was in the review. And this is the architecture of the two experiments that I've performed so far. So you have your raw audio data, you convert it to MFCC, and then for a simple CNN, I have a conv layer, max pool layer, a batch norm, fully connected, and then I embed it using displacement embedding, and then onto the quantum neural network. The second one is to use ResNet 18, and then the same quantum neural network. So just like the same process, raw audio MFCC, the ResNet 18, and then displacement quantum. But for the ResNet, because it is pre-trained on image data, which has the shape of 3224 by 224 on ImageNet data, we have to upsample the audio data. Our data set, which is one-dimensional, to be able to match it. So we upsample it to 1 by 224 in order for it to be trained on the ResNet model. Other than that, it won't work. So this, so for the experiment, we use Librosa to pre-process the data, where we add certain features to it and separate and then cut the length. I use PyTorch Lightning, which is built on top of PyTorch. And then the quantum part, we build a circuit from Pennyline from Xanadu, which is their machine learning quantum framework. And then we run it on the Strawberry Field simulator. And if in the future an actual Strawberry Field's quantum computer is available, we can run these experiments over there and see the performance. So like I mentioned earlier, the best way to encode data into a quantum circuit is still an open research, and you have to try to find out. So I use a displacement encoding, but there are other ways: basis encoding, amplitude encoding, and the likes. So for the first experiment, the data set that we use is like it's from Kaggle. It contains 5 famous speakers with a duration of 1 second and a sample rate of 16 kilohertz. But I took 2 speakers, Nelson Mandela and Benjamin Netanyahu, for binary classification. We used 25% of the data for testing and 20% of the remaining 75 for validation. So for the first experiment, this was a result. The classical ResNet had 98%, and the simple CNN had 92%, and the ResNet plus the quantum network didn't perform very much. So this led us to find out why, instead of getting an advantage in the quantum sense, why is the classical framework performing better? That's why I come to the update. So then we use a technique called Mixup. Mixup is an augmentation technique. First of all, let's take it this way. Neural networks generally are trained on a particular training data set, but when they come in, when you test them or evaluate them in the wild, when the data you're evaluating has a slight different distribution, they tend to perform badly. For example, what we call adversarial attack. So Mixup was an augmentation technique that was developed by Facebook AI in order to counter this, to make neural networks generalize more. And we use the same approach to try to create a form of superposition which is a feature that quantum states have that classical ones don't have, which is like an object can exist in different forms at the same time. So we take two different data sets and then use Mixup to combine them to create a form of superposition. And this is the mathematical formula. So xi, xj are the raw input vectors from the 2 different data sets, and then yi, yj are one hot encoded labels. The lambda here, it's between 0 and 1, and it is sampled from the beta distribution. So after we apply this to the data, we can see that for the CNN, the simple CNN, validation accuracy rose from to 98%, and when we did on a test data, it was 100%. For the ResNet, also performance increased from 74 to 99% on validation and 100% on test data. The paper for this has been presented at the ICDSA conference, and the proceedings will be published in the Scopus in the Springer book series in Singapore. So the conclusion is that even though we have created a form of superposition which quantum algorithms are generalizing, it's not something classical computers cannot do right now. So in order to be able to have quantum advantage, we need to actually do further experiments in modeling data set that is actually hard for classical networks to compute. And quantum machine learning is still a promising emerging field of research, and I will entreat all of you to join us. These are my references. Not all of them, just some of them. Thank you. Any questions?
Thank you. Questions? How you can explain improving accuracy from validation to test?
I don't understand
Why?
your question.
why the accuracy improved here? Yeah.
Okay, so
On test is better than on
yeah.
validation.
Yes, so the whole idea for the mix-up approach is to help neural networks to generalize and not memorize. So if actually the training data set itself, the results was around, I think 84 for the CNN and then like 75 for the ResNet. So the mix-up technique is for generalization, and this shows that the model is able to generalize properly when we applied mix-up.
So it's mainly mix-up contribution, you suppose?
Yes, because the
How much?
initial results without mix-up did not perform much better.
How many items in test set you have? How much data in test set? Five speakers, 1 second sample rate. So you wrote only percentage, but how many?
Okay, so I think it was 750. That's like 25% of 1,500. So 750 for each speaker. So combining them, the two of them, yes, will be like 1,500. So mix-up actually adds more data to it to increase the space. I would have to refer to.
Yeah, mix-up is actually they add only during training. During test,
yes. So I think it really increased. The actual data set was 1,500, and it actually increased it. I would have to refer to the code to get you the actual number. So after that, taking 25% of it for one speaker was 750, and the other speaker was 750, and combining them was 1,500.
Okay. Other questions? It seems very interesting result if it's 100% on test, even with validation later.
Yes. So I think actually right now what we are trying to test is like instead of applying mix-up directly in classical in the data set, we are trying to see if we can apply it in the quantum circuit itself. But as of now, it's been a pain, but we are hoping that we can get results. But that's just a trial, an extra experiment we are conducting. So.
Okay, if we trial already 100%, then it's promisable. Okay. If no questions, thanks. And
Thank you.
Pass to the next presenter. Maxim Kachanov, please.
Okay, just a second. Can you see my screen?
Yes.
Yes.
Just a second. How can I make the full screen? F alone?
on the slide button.
Or bottom right corner.
Yeah, the one.
Well, let's start. Theme of my diploma is application of segmentation algorithms to predict patient survival. My scientific advisor is Walid Koliai, and let's start. According to the Ministry of Health of the Russian Federation, the mortality rate from cancer in Russia is currently more than 200 people per 100,000 of population. At the same time, 70% of those who died from oncology have tumors in the brain. The most common method of primary detection is MRI. At the moment, the level of data processing specialists must be extremely high in order to minimize the factor of human error. One of the possible approaches to solving the above problem is the development of new diagnostic methods based on artificial intelligence systems. Thus, the goal of this work was to create prototypes of a system for detecting brain tumors in personalized diagnostics and then predict the human survival. As a rule, the result of an MRI examination of what? Can you hear me properly?
Yes, we can hear. Yes,
Can I continue?
participant. Yes, you continue.
Okay. As a rule, the result of an MRI examination of a patient's brain is several medical files of the DICOM format with continuous or sliced MRI images of the brain. Also, the patient is removed in several sequences or MRI modalities. There are T1, T1C, T2, or T2 flare. In the course of the presented work, data from the International Competition Brain Tumor Segmentation Challenge 2020 were used. In the pictures, you can see an example of marked representation in the 3D slicer tool for visualization and markup. And here you can see marked regions for masks. One is peritumoral edema. The number 2 is the tumor, and number 3 is necrosis. Unfortunately, files in this format are not suitable for training algorithms. From the continuous presentation of medical files, we pre-process the data pulled out individual slices. 2D images stored in familiar format, .png. After processing the data and forming pairs of the form, MRI image and mask, we got a ready-made dataset for trainer segmentation algorithms. The dataset consists of MRI images of 369 patients, and total images is 57,195. And I should say that all of these images are in training dataset. Also, I have a validation dataset, which I got from my scientific advisor, and this validation dataset is a result of segmentation of laboratories networks. And in this work, for the segmentation of brain tumors, several existing approaches are used. UNet Ternau's-net, DeepLab version 3, and Fix-to-Pix. And we will measure the quality of segmentation using the Soren's dice coefficient metric. The coefficient works as follows. Two images are taken, the number of matching pixels is calculated, multiplied by 2, and divided by the total number of pixels of the two images. The coefficient ranges from 0 to 1. And if coefficient is near to 0, is very bad, and if it's near to 1, it's pretty good. And now I wanted to tell you something about my architectures. UNet was taken as a baseline. It is considered one of the standard and one of the most popular convolution network architectures for image segmentation tasks. The UNet architecture is shown in the slide, and it consists of decoder and encoder, as you know. Ternau's-net is the UNet in which the encoder is represented by ResNet 18 neural network. The feature of DeepLab version 3 is at first is architecture developed by Google, and it uses extended convolutions or at-rows convolutions. Unlike classical convolutions, the kernel of extended convolution is split into fragments, the distance between which is set by the rate parameter. Examples of the extended convolution kernel are shown on the slide. And now Pix-to-Pix. For image segmentation, we can consider not only neural networks which specialize in this. Let's look at the segmentation problem a little more broadly. The result of segmentation is an image, which means if the neural network does not segment the brain tumor, but generates an image of the tumor and compares it to an MRI image, when, if successful, the result of generating this image will be the same with the result of segmentation. Such a task is called image-to-image translation, and the neural networks that solve it are conditionally adversarial generative. The conditionally adversarial generative network we have chosen is called Pix-to-Pix. After analyzing the solution presented above, the most effective was chosen. We need to carry out some experiments for models. During the first experiment, the error function was established, with which each architecture will achieve the maximum possible coefficient and dice coefficient. Error functions were chosen from the following set on the slide: is dice loss, binary cross entropy, and focal loss. I need to say that it's linear combinations of these losses: dice loss, binary cross entropy, and focal loss, as you can see on the slide. And first architecture for our experiment was UNet, and the best loss function for UNet was linear combination of binary cross entropy and dice loss with coefficient 0.3 and 0.7. UNet was UNet had learned for 50 epochs, 3 models of UNet, and the best model had this loss function and got the dice score 0.795. You can see on the screen that our problem, our models under overfitting. You can see it on the first and the second picture, because the loss is going up and dies going low. But for this issue, I was made some dropouts in classical UNet and early stopping. That's why the best, when UNet got the best dice score, you can see it on the first picture, it's nearly to 6 or 7 epoch. I saved this model, and that's why my saved model is not overfitted. That's it. The second architecture is DeepLab version 3, and because of long learning time, I needed to learn these models just only for 10 epochs, but even on this small number of epochs, DeepLab also made overfit, and I also made the early stopping. The best loss function for DeepLab was linear combination of binary cross entropy and dice loss with coefficients 0.5 and 0.5, and best dice was 0.787. And Ternau's-Net, it was worse architecture by the dice score. The best dice score was 0.729, and and you can see graphics of learning these models. And on this slide, you can see results of the experiment. The first picture is the MRI, the second is the original mask, the third is the mask segmented by UNet with dropout and with loss function, with the best loss function. And the fourth and the fifth are masks, which were segmented by DeepLab version 3 and Ternau's-Net with their best loss function. And a bit lower, I show you once again the best dices for my models. And for this experiment, we choose UNet as best model for now, and further we will work with UNet. And the second experiment is to find the best augmentations. We will choose from affine transformations, soft transformations, and strong transformations. Affine transformations include only geometrical functions, vertical flip, horizontal flip, and random rotations. Some soft transformations also include random brightness, random contrast, and random gamma. And strong transformations is much more broader. Is much broader, and it also includes shift, scale, elastic transform, grid distortion, and optical distortion. And the result of this experiment you can see on the slide. The fact is that the best augmentation for UNet was affine, and thanks to affine transformations, we've been able to get better dice score, and now it's 0.818, and it was increased. It was increased by 2%. On this slide and the next slide, you can see the result of segmentations of UNet with affine augmentations. It's pretty good, I think, but sometimes you can see that predicted mask is not really good, is not really near maybe to real. For example, on the last sample, you can see blue region, but in real mask, it's really tiny. You can see it if you will try. And now we need to we predicted masks, and now we need to predict survival. How long will people survive? For this, we have some pipeline, and you can see feature extraction, feature selection. Then we need to choose regression model and get survival days. For our data set, we have survival days. We got it from International Challenge, Brain Tumor Segmentation Challenge 2020. And our features we will extract from our predicted masks. For now, I could extract. I extracted features. I extracted 3,022 features, and one feature is 3,021 feature from masks, and one feature is age of people. It is also we get it also from Brain Tumor Segmentation Challenge, the age of people, and the last feature is survival days. We have now 2,036 rows because not to all patients have survival days. Just we don't know survival days for some patients, and that's why it is. And what I need to do further? I need to show you and any other people show results for Pix2Pix. I didn't do it because Pix2Pix, I had some troubles with this architecture, and I needed to relearn it. But I'm sure that it's for now. I'm sure that Pix2Pix is worse than UNet because I did some research with these architectures, but I just didn't show you the results because I need it to relearn. What else? I need to do feature selection. I did feature extraction. Now I need to do feature selection and find the best regression model. And it will be the end of my project. I will get the survival days. I will evaluate it, and that's all. Thank you. If you have any questions, I will try to answer it.
Thank you for presentation.
I would like to have a question.
Yeah, of course.
Yeah, thank you for your very good presentation. So I think I missed the first part. So could you please tell me again which data set you use for your thesis?
Yes, of course. I used data set from international challenge called Brain Tumor Segmentation Challenge 2020.
And during your experiment, did you train the model UNet and other models from scratch, or you just train a few last layers?
No, I trained the whole models on GPU, on 2 GPUs. It were NVIDIA GeForce 2060 Super and NVIDIA GeForce 2080. And for example, for UNet, for 50 epochs of free models of UNet, I needed near maybe 1 day. For 10 epochs of free models of deep lab version 3, I needed near 1 day and a half, and for TransNet I needed near 1 day too. But now I'm learning pix to pix, and I have trained it for 1 day, and it continues training.
Yes, so may I ask, where did you get access to the GPU? Did you rent it online or you have it yourself?
No, I asked my friends at university, and I got it from them.
Okay, cool. The reason I asked because
Actually, I should say that it's university university computers.
okay, okay. Thank you. And oh, sorry, one last question. So during your experiment, and then from your observation, what do you think the most important factor that we should focus in order to improve the model for image segmentation tasks?
Sorry, I didn't understand the question. Could you repeat, please?
Yes, yes. So my question is just asking your opinion. So when you try to do the image segmentation with different architecture, with different models, what do you think the most important factor that you should focus in order to improve the model performance? For example, you might think the data augmentation is more important, or the model architecture, or the hyperparameter, or the data. I mean, things like that. What do you think the most important?
I think that the most important thing is, of course, the data. You know, the data set of brain tumor segmentation challenge is pretty well, but it has a lot of mistakes, and because of it, we have a little bit dirty data set, and also not many people are ready to share their MRI to our people, to some challenges, and that's why we don't have a lot of data. We have only 369 patients for our trained data set. And as I said before, it's a little bit dirty and not very big. And that's why we have what we have. The second place is the second place of importance is, of course, the model. The model is you need to choose a model very carefully because of this data set, the models are often overfits. Any model often overfits. And maybe augmentations help us to get some regularization for our data set, and that's why we get better dice score, better result of segmentation. It's because of regularization of our a little bit dirty data set. Did I answer your question?
Yes, yes. Thank you very much. Thank you.
Okay, thanks for a lot of questions and answers, and thank presenter. And we're now switching to the last presentation for today. Sorry. Yeah, some comments you see from Virgilio, Maxim, and Kazinets. Roman, please.
Hey, can you hear me?
Yes.
I need to answer it in the chat or here.
No, maybe in the chat. Yeah, not now.
Okay.
Okay. Hello, everyone. My name is Roman. My scientific advisor Berik Vladimir Borisovich, and today I present my master thesis. It's analysis of CNN working with logical decision functions and the task of computer tomography images recognition. Okay, and let's start. So, as you know, CNN have achieved very great performance, and especially in computer vision tasks, but their complexity increased demand for maybe some explainable and interpretability of models. So it means what other than produce very precise some predictions, you also need to produce some explanations of decisions. So, and our study aims to solve explainability of CNN and try to create some classification network with clear or explicit reasoning. So our proposed method should have competitive performance to classic CNNs, and also it has high interoperability, but it's some difficult point because it's very hard to say the quality of interpretability because it has not some strong metrics about this. So also we try to create model with end-to-end session of training and inference. So it like one pipeline where you start and produce results without any post-processing methods. Also, our methods required only image level labels, so it only classes for images without any pixel annotation. Also, the general idea was based on reasoning like a human style. For example, so this object of class A, because it has some specific parts, some specific object parts, for example. And in general, our work consists of 3 components. It's CNN feature extraction, it's learnable back of visual words, and differentiable decision tree as classifier for our model. So patterns or prototypes, idea was taken from a paper that looks like that. It's the paper of 2019, as I remember. And the idea of this paper was to learn specific object parts and uses the score, distance score of them to produce classification results. So it means it's very similar like human thing. It split the whole image, the whole object into some regions and compare with some specific parts what was learned from a whole data set. And the image class is equal to the class of these specific patterns. So it means like this is the car because it have wheels, for example. And let's go next. So how it works? The proto-net consists of 2 parts. It's convolutional layers, CNN backbone, which extract features and produce the feature activation map with the size H, Y, and D, where H and Y it's the width and height, and D is the dimension of feature map. So it's depth of the produced tensor. And also, ProtoNet has specific layer, which named as prototype layer. It consists of number of learnable tensors, of learnable parameters, with the shape of 1 to 1 to D. So it can be represented as vectors with the same depth as produced feature map from CNN backbone. And for example, the produced map with of image with name of Z equal like f of x. It can be represented as patches or cells of image of whole image in some latent representation. So what pattern layer does? Each pattern, so each pattern or each pattern unit compute the L2 distance between all patches in feature map and particular pattern PG. And each pattern generates some distance map between activation map and particular pattern. And each pattern of all set of these prototypes generate new 3D tensor, where each slice it is a distance map from between feature map and particular pattern. Also, after this inner step, some activation function invert this distance into the similarity score and take max pool to take the best, the closest score from feature map. So in the output of a G prototype layer, they have number of outputs equal with the number of prototypes. And after that, in a protonet, these scores pass into classification layer, and after that, they got the prediction. So the second component, it's a decision tree. All of you know, I think, about decision tree. It's like a graph-based recognition model. It can do classification or recognition or regression, and consists of leaves and inner nodes, where in the inner nodes we check some feature and by threshold. It means what we compare some feature of object representation with threshold B, and for example, if feature of particular object less, we go in the left, or if greater, we go on the right. So it's a binary split, and after all routing, we came into leaves which have some of the targets. It's very this type of model have great interpretability, but has some problem. It's not differentiable and differential, and can be trained with neural network, and can be only used after training the CNN or DNN as another model. So, but the model solved decision tree tried to solve this problem, and this paper from Google team, and we produce the decision tree, like they produce neural network what mimic the decision tree, and it can train like a standard neural network by some, for example, SGG optimization, and how it works. So as the decision tree, this model has inner nodes and leaves, and in inner nodes, it have filters like in a standard linear fully connected layer. So it take input X, for example, it can be some features, and produce the probability. So it apply filters on input signals, and followed by sigmoid function. So in a right node, it produce the right probability, and on the left, it produce the probability of left branch. It means what in a training, each data point go through all nodes from through all branches with some probability, rather than binary selection, binary splitting in a standard decision tree. And in the end of this tree, it has some learnable distribution, learnable static distribution, like the tensor of the length as the number of classes. So during training, it all probability tree learn there's some nodes distribution and leaf distribution. So it's general. It's some. It's like the hierarchical mixture of leaves where their weights the probability to these leaves. Yeah. As example, it's a picture from original paper. It is a tree trained on MNIST dataset, which consisted of handwritten digits. And here we also provide the class splitting between branches, between nodes. So, and our work compose previous two components in one model. So it is the first generation and consists of CNN backbone and pattern layer and also soft decision tree. But in this type of model, in each node, we learn pattern or prototype. So in general, each node take as input the feature map from particle image and produce similarity score to the output. This similarity score go to the right with the similarity between the closest patch from activation map and the particular pattern, and on the left they go from inverted like 1 minus this similarity score. Yeah, and the second version of our method, we double the pattern layer and modified the node structure. So how it look like in a more close. Each node has try to learn two patterns, and in input it take the feature representation of image, and after that it compute two similarity maps between the whole feature map and each of patterns, produce two map, and after that it produced probabilities between these two nodes, between these two patterns, by applying softmax on inverted distance between left and right. So it means what each branch now specified by some specific filter, some specific pattern. So training now trainings consist of two stages. Like first, it is initialization. We initialize some CNN backbone. It can be done, for example, by transfer learning. For example, we create a pattern layer and soft decision tree with some depth, and continue the third stage training. In training, we simply minimize the cross entropy between weighted leaves and define targets of dataset. On the second stage, we provide projection step. The projection step, it means what we assign as a pattern in each node the closest patches from training set. And because of that, after we can make some visualizations of the training. So one of the experiments was on animal dataset. Original animal dataset consists of 10 classes, but I took 5 of them. Whole training size consists of 30,000 and test size consists of 250. So I used some standard augmentation like in a his CV space and some flipping and random rotations. So the results provided here show what, for example, neural pattern tree 2 very close to the classical approach like ResNet 50, and ResNet 50 was used as a backbone in a neural pattern tree 1 and neural pattern tree 2. The depth of above 3 was the 5. So, oh, sorry. In a picture here, I provide subtree of training global decision. I can't show a whole tree because it's very big and I couldn't place it in a slide. But here we have the tree with 2 branches in each node, where the right it means how this pattern exists, and in the left how it absent. So in general, these patterns was like concentrated on some specific parts of animals. Yeah, and also I provided the local decision on some image, on some example image, and it's very clear how this network provide decision. So it means that some of patterns exist or some not, and if it exists, it provides what of the patterns and where it provided on image sample. So, and what about of the second version? I also provide here the global prediction. It's a subtree of the whole decision. It provides double patterns in each node. And what the problem of first version was what I got what in some classes specified only how absent. So for some class was no patterns. So the second generation solved this problem and generate patterns for left and right branches. So I haven't provided the local decision because it has some code problem and I need to refactoring. And what about the second? It is the hemorrhage classifications. The data was taken from Kaggle competition like RSNA interrectal hemorrhage detection. Data set consists of CT images from 5 classes. It's the brain, some kind of brain damage, and the target train size was 41,000 images, and the test size was 500 images. Also, image was resized in a target size of 224, and images was preprocessed by image windowing to produce 3-channel image in a BrainSoft and subdural window, and some standard augmentations like a flip rotation and cropping was applied in a trained dataset. For now, it's still training on my machine, and after 20 epochs, I got this kind of results where like the neural pattern tree number 2 is leading on test and training set in accuracy metric. And after neural pattern tree number 2, the classic ResNet approach outperform the first version of neural tree. So after training was completed, I provide some visualizations of predictions. So, and this proposed method required maybe achieve some comparable results. In theory, it requires less parameters than ProtoNet, but I haven't done comparing, and it's my next step on this week to compare my results with ProtoNet and provide results maybe. So, but theoretically, it must outperform the ProtoNet, as I think. So this model have some explainable features and I think clear classification process. So this is all for now. Thank you for your attention.
Thanks for presentation. Please, questions?
May I ask a question?
Yes.
Thank you for your presentation. It was interesting. I have a question about your work, about your example with animals. Can we use map as feature of class? So can we use this approach in zero-shot learning, for example? So can we provide some set of maps for new class and use without retraining our net, or no? How you think about this? What you think?
Can you again? I have bad conditions.
Can we use approach with some map features? Yeah, that's in.
You mean can we take some predefined net and use this activation map like in pattern learning?
Yeah. Can we use pattern learning as description of class, for example?
I think yes, because we can freeze the CNN backbone and learn only these patterns, this classification.
So we can combine some maps and receive new class, for example.
I think is in general, yeah, but I haven't tested this.
Okay, thank you.
Other questions? Okay, thanks for presentation, to Roman, and thanks all for participants in today's seminar. See you next time.
Bye.
Goodbye.
Goodbye.
Bye.